Welcome everyone to the Hudson & Thames Reading Group. I'm Michael Strubeff. I'm the CEO of Hudson & Thames. This is, I think, my second reading group presentation that I've done. It's on a topic that I've found fascinating for many years now, and I'm really excited to actually be able to give this talk. We'll be talking a little bit about reinforcement learning, particularly in finance, and we're going to be doing that through this library called FinRL. That's kind of been put out in the last couple of years as an easy way to get started inside of the financial domain if you want to do reinforcement learning. As always, I like talking about this kind of stuff, and so do we here at Hudson & Thames. So please follow us on Twitter and LinkedIn. You can always check out our website. But yeah, so without further ado, let's get stuck in. I think as a surprise, we've been chatting offline a little bit. That's just quite interesting. Is since this is a AI themed talk, there's going to be a couple of surprises built in, which I think will be interesting. We'll be looking at a whole bunch of cool developments in reinforcement learning. But in terms of generative AI, our typical architecture photo, which we have on the right-hand side of the presentation, this time around, that has actually been generated by AI. You can tell because over here on the right-hand side, in the steel and the glass, there's a little bit of a weird warping going on, but it's pretty astounding how good these things are getting nowadays. And I generated this one myself. So this was done using Midjourney for those who know of it. But anyway, let's get started into FinRL. So I wanted to cover a kind of brief history of reinforcement learning before we get stuck into what FinRL brings to the table. So this all started in the 1950s when we had a description of states, actions, and environments. And essentially this problem-solving decision-making problem got described in what's known as a Markov decision process or Markov decision processes. And this is kind of the foundational mathematical layer that models decision-making problems, right? It talks about states, which is states that both the actor and the environment can be in. And it talks about actions that these agents can take and also how these environments kind of respond to these actions. And then in the 1960s, we started talking a little bit more about reinforcement learning concepts. So we started talking about, reward systems and punishment systems to kind of irk an agent to learn how to solve certain problems that require decision-making. So it's kind of like the carrot and the stick psychology that we started looking at to develop this theory further. Then in the 70s, we started looking at trial and error algorithms that incorporated, temporal difference. So it started tracking actions over time and how when we interact with problems over time in a certain environment, how can we use, past experience to guide us in the present? Then Q-learning came along, which is a set of solutions that kind of solve Markov decision processes. And then in the 2000s, we got deep Q-learning, which is where we started using gradient descent and deep networks and deep learning to try and, discover these optimal policies and to make Q-learning better. In the 2010s, perhaps most famously, we got AlphaGo, which was the first time a computer essentially could beat a human at the game of Go. It was a very widely publicized and controversial kind of moment in history. It's quite a watershed moment for reinforcement learning, almost as big, you could say in that time, it's almost as big as what ChatGPT is for language, natural language today. There's a great documentary that's freely available for when DeepMind did this. So you should go check that out. And this has been generalized into a model called Mu0, where it doesn't even have to know the rules of the game. It can kind of generalize to almost anything, not just the game of Go. And it's quite incredible. And over here on the right-hand side, this is just an example of, how the classic Atari game Breakout, how a model can learn essentially how to actually play and win the game. And you can see it starts off kind of rubbish. And as the number of episodes and training episodes get better and better, it starts learning strategies. And, we've been able to solve a lot of problems that we thought previously were completely unsolvable using reinforcement learning. So before we kind of dive straight into the practical stuff, it's really important to talk a little bit about the concepts of reinforcement learning. So in a nutshell, you have this diagram over here on the right-hand side. You have an environment, which describes a state. And this gets fed into an agent, which observes the environment, so to speak. The agent can take some kind of action based on the state of the environment. And then the new state plus a reward signal gets sent back to the agent. So the policy, there's this thing called a policy. That is what allows the agent to map the state and the reward signal into an action. And sometimes we also use what's known as a value function, which the policy kind of tightly integrates with, which helps allow the agent to estimate the potential future reward of the current state or a future action. So it's not just about mapping my state to an action. It's also maybe deciding, hey, if I were to take this action, or if I am in this current position on, let's say, a chessboard, is this a good or bad position to be in? All of that kind of comes into play. And the agent essentially works to maximize this value function. And the whole goal of reinforcement learning is, how do we train a good policy that allows us to take the right actions in order to maximize this reward? So there are a whole bunch of algorithms for policy optimization. It's basically an algorithm zoo, really, and each has a different philosophy, a different set of ideas. I must say reinforcement learning has got some of the most creative ways, I must say, of trying to coax these agents into understanding things. It's really fun to read a bunch of the papers on how these agents kind of conceptually work. I think the reason why that's fun is there's also so much literature on trying to, train people, all of those kinds of concepts. There's a lot of game theory and how educating players in video games. All of those ideas can kind of quite easily be encoded in these agents, which is very cool. And also why I think there's such a wide kind of variety of different approaches. But there are three kind of, or four rather, categories that emerge from this. So you have value-based philosophies. This is where you kind of try and estimate the value of each state or state action pair. So you try and estimate, given a state, my current state, and a possible action, how much value will I generate? And that's what you use to make the decision. Then you get policy-based optimizations, which try to optimize the policy without trying to figure out what the value is of my current position. We're not trying to predict reward. We're just trying to understand, okay, I know in the past that if I take certain policy, I take certain decisions given a existing state, I've gotten a reward. So I'm just going to do that. And then you get model-based. This is quite interesting, especially in the world of robotics, where the agent will attempt to build a model of the environment and then use this to plan. And then, of course, you can get these kind of, you start marrying them. So you get actor-critic, philosophies, which combine both the value and the policy-based methods. So what you have is the actor, which is, it's trying to figure out which action it should take. And then you have a critic that evaluates the current state and the actor and the decision that the actor is evaluating. And the critic will then kind of be like, are you sure you want to do that? Do I think that's a good idea? And so you can use the two, and you actually train the two different networks together in order to get both better at predicting how effective a certain action will be, and also at making better decisions, almost like a teacher-student dynamic. But the main point I want to make is that there are so many of them out there. And but that being said, there are some harsh realities with reinforcement learning. Let me just make sure my slides are correct. There we go. There are some kind of harsh realities with reinforcement learning. And, reinforcement learning tends to be very successful, actually, if you can get it to work. So there are a lot of pitfalls with reinforcement learning that make these models, out of all the different types of models to train, training agents is particularly difficult. So you have the exploitation versus exploration kind of trade-off that's quite difficult. How often do I try a new strategy? That's the exploration. Or do I just stick with what currently works and just exploit that? And so a really funny example of that is this Coast Runners demo here, where the actual goal was to train a speedboat to race through the course as quickly as possible, which would give them the maximum amount of points. But what the agent discovered is, if it just got into this loop over here and just kept on picking up these kind of turbo boosts, it would boost its score. And so it just kept on doing that, over and over and over again, instead of actually doing what you were supposed to do. So that is, the exploitation versus exploration issue, but that's also an issue with, sparse or delayed rewards. If you think your reward signal only comes right at the end when you finish, this kind of course, that's a lot of actions to take before you can actually figure out which actions are good or bad, right? The other thing is also you get reward function failure. So that's also what's going on in this little demo over here. For those who know about Goodhart's law, which, paraphrase essentially states that if you set any kind of metric that you will use to judge people's performance, they will just game the metric. These agents are extremely good at doing this, and that's kind of what happens there. So you have to be very careful. They're also very sample inefficient. It takes way more iterations than you'd expect to actually get good. And of course, you have lots of instability and really low levels of convergence. And when you aren't unstable or have low levels of convergence, you can overfit on problems really easily as well. So, reinforcement learning in many ways is quite unsolved quite literally. And there are a lot of things that make this difficult. So it's an open field of study. It's lost a little bit of its momentum, I think, over the last couple of years with large language models kind of taking the spotlight. But I'm expecting, and I hope that more attention will start returning to reinforcement learning. But I always get the impression it's like, wow, this is so hard that we've kind of given up for a little bit. But, if you look at some of the robotic stuff, these guys are really interested in this. So it's a very active field of study and quite exciting. So speaking of algorithms, for the curious, here's a list of them. I've linked to all of their papers. It's fun to read these papers. They're actually not that hard to understand, at least the conceptual level, but I'm going to skip over this slide. Okay, so let's talk a little bit about the reinforcement learning landscape, for users like you and me. So like we discussed, you kind of need environments, then you need agents. So just the de facto environment is the OpenAI Gym. I've linked to it there for you guys to take a look at afterwards. It provides all of these kinds of fun, different problems for reinforcement learning agents to solve. So here's one where you have to land this little spaceship, carefully. There's another one where you have to train a biped to walk. It's a lot of fun, and there's a lot of really well-defined ones. And that's kind of just become the de facto. It's really well-defined. It's got good documentation, lots of examples. This is what we use to define our environments. And then for agents and policy optimization algorithms, these are the three big ones that uses. So they're stable baselines, elegant RL, and RL-lib. There are lots of others as well that have, lots of users and big communities around them. But those are the three that FinRL uses. And it shouldn't be too hard to expand them, because since these environments are the OpenAI Gym environments are considered almost the de facto one, almost all of these will have drop-in APIs that allow it to work with that. So that's good news. Point is, the tooling is out there, and it's really good and quite mature. So where FinRL fits into the picture is it's trying to do what all of these libraries are doing, but it just wants to make it specific to the financial domain. So the key thing is they define financial reinforcement learning environments based off of OpenAI Gym. And then they make it really easy to drop in agents from elegant RL stable baselines and RL-lib into these environments, and then just let them loose and let them train. If you read the paper, there's a lot of marketing around the kind of 3-layer approach. But in a nutshell, look, it's just, we've got kick-ass, financial environments, and we also make it just easy to use all of these agents from these different libraries. And what's cool is it actually kind of works, but I'll talk about that a bit more when we go to the demo. Yeah, so just briefly on the 3-layer architecture, right? It's an application, agent, and environment sandwich. Perfectly honest, I don't think there's another way of doing this. I don't know why they hype this up so much. And in my personal opinion, there's very thin wrappers over these agents. I think where the real value actually lies is getting started is in these market environments. So they've done quite a good job of setting those up. But there are some pitfalls, but we'll talk more about that later. Okay, so let's talk a little bit about these environments that FinRL brings to the table. So there's 3 main ones. So there's stock trading. Then they have a couple of mutations. So you can, penalize the agent for holding onto cash. You can give it stop loss, criteria, that kind of thing. Then there's portfolio allocation, so broader than just stocks. And then there's also cryptocurrency trading environments where you can just trade Bitcoin, but also multiple cryptocurrencies. All of these are quite similar, so it's not too hard to see how you could, pivot from one to the other, but that's what's available right now. I will say though, as a personal critique, there's a lot of inconsistencies in the way things are actually defined in the code, and they're not super customizable right now, especially in the reward function. So I believe the stock trading environment that we're going to look at, what it actually tries to reward is I could be wrong, but if I got this correct, is the actual total value of the portfolio at the end of each day. But maybe you want to change that reward function to minimize risk, or maybe you want to change that reward function to maximize the Sharpe ratio, things like that. So there's not that much customization yet. If you want to do that in an easy way, what you have to do is hop in and actually change the code of FinRL. It's not as bad as it sounds, but it's just something, that you have to keep in mind. But anyway, that's more just of a subtle critique. And I think something with the library can be improved. And to be fair, it is open source. So maybe I should contribute a fix. But speaking of code, let's talk about that as well. So it is research code, and research code is research code, right? I've written research code. I think anyone who's kind of done something academic will have written research code, and it tends to be bad. And luckily, FinRL is really not bad at all, but it is still research code. So there are some challenges, I think, that prevent FinRL from being as good as it could be. The documentation is really lacking. You'll need to read the code to understand what's actually going on under the hood. There's lots of commented out code blocks. There's not the greatest kind of software engineering practices. For example, there's a unit tests folder, but there's no real unit tests. But that being said, it's cobbled together, but it does seem to work quite well. And what's interesting for me is I always thought of this as quite a difficult kind of thing to actually set up and get going. But my recommendation after actually having dived into their code is use this as inspiration, but roll your own, because FinRL proves it's actually a lot easier than you think, especially with, both the agents and the environments that are out there today. So I'd actually encourage people to dive into the code base. It's not as bad as you think. Okay, so time for a demo. This is always the fun part, I guess. So I'm going to run through a FinRL demo. I'll be using the stock trading environment. So we're going to trade some stocks. We're going to train a range of agents. Well, I've trained them already. They're probably still running in the background. We're going to compare them to both a index and also using mean variance optimization, classic techniques to optimize your portfolio. And then we'll test all of the methods on out of sample data set and compare them. And I've got a bit of commentary about FinRL as we go, and I'll just do that at the same time. So without further ado, let's quickly hop into the demo. Okay. Now, things are a little small, so let's try presentation mode. All right, I'm hoping everyone can see my screen. So this is actually a demo that I've put together. It's based quite heavily on their examples, but I've tweaked it and added in some explanations and actually changed the way they do some of the stuff just to make it a bit clearer what's actually going on. So I would actually like to make this available to everyone after the talk. So just keep that in mind. So let's start at the beginning. You import a whole bunch of stuff from FinRL. Basically, what we're going to look at is 30 DAO, the DAO 30 tickers. So that's these over here. We set our train start and end dates and our trade. These are going to be our actual testing out of sample data. And they have just a nice convenience method to pull this down and get us a data frame of the daily, pricing of all of these ticks that are listed over here. And then we do some data prep. So FinRL has a bit of built-in functionality to allow us to do this. They can do things like adding in technical indicators, adding in a turbulence index. These are optional depending on your philosophy. Some of these can be, ignored. You can skip this step. You can augment the data frame with your own features as long as you put the dimensionality correctly, which I'll show you later. But the idea is I've just decided to stick with these just to kind of stay in tune with the example notebooks that they have. So they have a nice little feature engineer class that allows us to do this. It adds in all of our technical indicators and some of our, turbulence measures and stuff like that. This is quite funny because there's this feature called user-defined feature, which presumably I thought would be a way for you to define your own features, maybe by passing in a function. It turns out, no, if you set this to true, it just adds in a daily return as a feature. Yeah. So, I would just kind of point that out. It's a bit janky. So just be careful when you're playing around with these things, really kind of make sure it's doing what you expect it to do. And I mean, even here, I wanted to see if we could find out what that user-defined feature flag is about. So I looked up the doc string and it isn't very useful at all. So anyway, the other thing also that I've just pointed out here that's not in the example library is that you need to do some very specific pre-processing because FinRL really expects the index of the data frame to be in a very specific way. I've actually isolated it to the source code. There's a very particular line over here where they cause the trouble. But once again, it's open source. I can probably propose a patch to get that sorted out. But anyway, I'm going to skip over this. Essentially, what we do is we just reformat the data frame to have every single one of the dates with each of the ticks, and then their open, high, low, close, volume, and then all of the technical indicators. And then what we do is we split this up, right? So we have our kind of training set, and then we have our test set. Okay, now comes the important part. We need to define the environment. So we define the dimensions. So we're going to be able to train, we're going to be able to have 30 stocks that we can trade. And then we have to define the state space. It was pretty interesting here. I'm not entirely sure why we need 1 + 2 times the stock dimension plus okay, it makes sense to have the indicators per stock dimension, but I'm not sure why we're 2 times the stock dimension for the state space. I'll have to read up a little bit more about why we do that, but this is just what you have to do. And we can also input things like the transaction costs, right? So the buy cost and the sell cost. That's pretty cool. We just set it to 0.001% for all of the shares. And then we start off with only capital, right? $1 million in capital, but no shares. So our initial portfolios, we start off with just cash. And then we kind of pass in all of the environments. The interesting thing is this HMAX is not explained at all in the docs. It's not even explained in the notebook, I don't think. I managed to find out that this is the number of shares you're allowed to buy or sell per asset at any given step. So yeah, here we just look up the kind of environment again, and we see that there's very little explanation of what these things are. You really do have to dive into the code. But anyway, we create our environment and away we go. So now what we have to do is we just have to import our agents. We set up the environment, and it's as simple as this, right? We just say, for my agent, which has the training environment, I just get this model, which is that A2C model, which I linked to in the presentation. And we want to train it using the, I'm guessing MLP stands for multi-layer perceptron policy. Could be wrong. Don't quote me on that. But I believe that's the case because there will probably be a CNN policy as well, but that's besides the point. And we just set up some pathing to store the results, and that's it. Now, the only thing we have to do is call this .train model method and pass in our model where we want to log the number of time steps, and away it goes. And, we can kind of fetch the results, and then we can take a look. So here I'm plotting the entropy loss, and we can see how the loss is actually going down, which presumably implies the model's getting better as it goes. And we can do exactly the same code just for all the different types of models, right? So we see we've done it here for this DDPG agent. And we can see over here how it seems to hit a plateau very quickly in terms of its actor loss. We do the same thing with the PPO agent. Also see how the entropy loss kind of declines over time. And we do the same thing with the TD3 agent also. I think the only thing that's really important to note here is that I've trained a single agent on a CPU for only 50,000 time steps. And we already know these things are very sample inefficient. So when I talk about the results a little bit, it's important to keep that in mind. But it's quite impressive that I can train an agent that will at least make attempts at trades in, half an hour. That's really cool. And then what we do is we just take our trained model. We now set up our environment to only have the testing data. So in other words, our out of sample data set, and then we just score. We get the models to kind of run predictions and take actions based on the new data set, right? The new environment. And when we plot these out, this is kind of what we see, right? So we can see it looks like, TD3 tends to be quite good most of the time. PPO does a little bit worse, but then catches up and actually ends up being, more or less on par with TD3 at the end. But anyway, so this is cool. This is how the agents trade. But I think it's really important to take a look at how they would compare to something like mean variance optimization. So we take, our training data set, we calculate the stock returns, we do the usual thing where we will work out, our mean returns across all of our assets, the covariance. Here's a nice plot of that. And then we use the pie portfolio to kind of figure out an optimal portfolio allocation. So that's what we get over here. And then what we also used just as a reference point is we use the DJIA or the Dow Jones Industrial Average Index as a point of comparison. And this one's luckily quite easy. We just fetch that from Yahoo. I wanted to plot the final results, but it seems like I have a mistake here. So what I'm going to do is use one that they prepared earlier, which is here. So, or actually, let's do this. I think I actually have one from earlier that I looked at. All right, so here we can actually take a look at how things performed. So we see that the mean variance optimization actually did end up, at the end when we were done, performing the best at the end of our test. But what's interesting is like this example actually includes all of the various agents. A lot of the agents, depending on where you cut things in time, right, actually seem to do better at certain points in time. And so this is quite interesting how you can kind of compare them. And what's interesting for me is this pink line, that's the index. And so you actually see we have quite a lot of agents that are able to outperform the index, which is, really, really interesting and quite impressive. In their example that they actually use, so this was a really kind of impressive run. I'm not sure quite how they managed to train this model, but in this case, their ATC outperformed, the mean variance optimization model by, what's that? Like, huge amount. So, depending on how these agents are trained, and obviously, I mean, one of the things I've not, done at all here is hyperparameter tuning. We've not looked at engineering additional features. We've not looked at training multiple agents, ensembling agents together. We've not looked at any of that. All we've done is literally in half an hour, I've trained a couple of these, and you get out strategies that are, different and unique. And what's fun about this as well is over here, let me just find it for you quick. When we do this prediction step, we actually get the actual actions. So if we just had to look at what ATC did, we actually get the actual actions for which shares were bought and sold at each time step. And you can kind of see kind of how the asset allocation took place. And I think analyzing that could actually be quite interesting, especially if you can correlate it to results. But yeah, that's just a really quick demo of how easy it is. It takes you probably a day to figure out how to do this, which is extremely impressive. Cool. And that kind of brings us to the end. So I think I just want to do a bit of a recap and draw some conclusions and maybe provide some of my thoughts, which is something I with these talks tend to be fond of doing. But basically for me, reinforcement learning is really cool and really awesome. In my opinion, and I've thought this for a while, so it's fun to kind of touch on this again. I do think reinforcement learning is going to change the world. To be fair, it has already, just, looking at AlphaGo. We are already at human level performance in first-person shooter games in complex environments, which is incredible. So here's a nice little study that DeepMind did that you should go check out if you're interested. But what's interesting for me personally, and why I think finance is probably more exploitable than other environments, because I mean, think about it, trying to design a robot to do plumbing or do cooking, that's hard. There's so many variables there. But in many ways, finances and markets are an almost ideal environment. There are very well-defined rules, very well-defined actions, and very easy to calculate rewards. It's a lot easier to calculate, or to have the return of a portfolio be your reward signal than, is this, if you were like creating a cooking robot, is this egg perfectly fried? It's kind of like, that's a lot more tricky. But in the finance world, we have, we're data driven. We have really good signals. The industry is built on signals in many ways. Besides that, also in terms of FinRL specifically, the accessibility is quite special. It took me a single day to get going, even if it's a bit hacky. And I was training on a CPU. Obviously, all of these run on PyTorch. Some of these agents will run on TensorFlow. And you can train these using a GPU in a massive data set if you wanted to. And it's pretty cool that you can outperform the index using a CPU and, 30 minutes from scratch with an agent that knows nothing. That's quite incredible. And so my kind of conclusion and recommendation from me personally would be that I don't think we should dismiss this. I think potentially this could be a way of discovering novel strategies. In some ways, I kind of want to dream in that direction. I think it's quite interesting. But I think a key reminder here is, people thought a computer would never beat a human at chess, never mind a game like Go. And that happened. And that happened 10 years ago, right? And agents have already shown they're capable of perfecting human learned behavior. So, for those of you who are fans of Quake, agents have already learned strafe jumping as techniques. If you've played Dota or Dota 2, they figured out how to do creep blocking. They do these kinds of techniques that are things that humans took a really long time to figure out and perfect. And they can, we just throw computed the problem and they figure it out after a couple of days. It's extremely impressive. And I see no reason why finance would be immune from this, in my opinion. But what's also quite fascinating, and that's what I alluded to earlier, is agents have actually discovered novel strategies. And in, the domains of chess and Go, humans are actually using the strategies that have been successful that these agents have discovered to help them improve their own level of understanding in these kind of domains. And the fact that it's already happening at ultra competitive settings, as if the finance industry isn't ultra competitive, I think there's some lessons and conclusions to be taken away from that. So I really recommend, if you're curious about this at all, read up a little bit about reinforcement learning, download FinRL, give it a go. It's actually a really fascinating package. And I think it leaves a door wide open for what can be done. And I would love personally to see what would happen in terms of how good can I get these agents with a little bit of hyperparameter tuning, a bit more experimentation, and maybe tweaking that reward signal to be a bit more reliable. But yeah, so that's basically it. Thank you very much, and I hope you enjoyed it.